We present ROM, robust and object-aware motion generation using neural pose descriptors. We generate character animations for human-object interaction conditioned on a goal pose. Our method is robust to objects unseen during training. In contrast to previous methods, we only require one object paired with motion capture data and leverage a library of shapes to optimize for a goal interaction pose. To obtain the goal pose, we provide a reference pose on reference chair and optimize it for unseen chair provided during inference. The animation on the right shows the optimization process starting with the reference pose projected to the nearest new chair surface. At the end of the optimization, we obtain a goal pose that adapts to new chair geometry. Neural state machine is a related work which focuses on human-scene interaction. To generate seating motion on new chair during inference, it requires annotations such as joint contact labels and seating orientation. The video on the right shows that if the orientation is wrongly labeled, neural state machine generates a seating motion that disregards the chair geometry. SAMP generates stochastic motions without the need to label contacts and orientation. However, it is susceptible to implausible motion and inaccurate direction prediction. Couch is another related work which studies human-chair interaction. It proposes a contact net which generates hand contact points on the object. However, it needs pre-annotated chair orientation, and we found contact net not robust to unseen chairs. In addition, all the methods require data augmentation, which swaps real chair with synthetic chair each frame. The edited motion curve after contact projection could lead to unnatural movement and jittering. In contrast to previous methods, we propose an animation framework which generalizes to unseen objects with limited mocap training data. The input of our system is the current character state, and we auto-regressively generate the next state until the character performs the intended action. Our method consists of SPD optimization and l-NSM. SPD stands for skeletal pose descriptor. It generates goal pose for our motion framework, l-NSM, which stands for light neural state machine. l-NSM is trained on mocap data with only one object for each action category. We train SPD on the chair and sofa categories in ShapeNet dataset. SPD optimization generates an interaction pose on a novel object. It takes a reference chair, reference pose, novel chair, and novel initial pose as input. Novel pose is updated during optimization until it converges to the corresponding goal pose on the novel chair. We design a three-stage optimization process for goal pose synthesis. In the first stage, we only optimize root translation and orientation. In the second stage, we optimize all degree of freedom. In the final stage, we add the regularizers for pose refinement. We visualize the optimization process with the same reference pose adapting to various target chairs. With the same reference pose, the goal pose varies according to different sofa geometries. This animation shows that we are robust to scale changes. The skeletal pose descriptor is SE3 equivariant. It is robust to orientation perturbations. Next, we show an ablation study of SPD optimization. The animation on the left optimizes all degree of freedom simultaneously. It leads to twisted joints. The second animation removes the angle constraints. The third animation removes the pose regularizer. The last visualization is our proposed approach. We empirically find that it generates the most realistic seating pose after testing on diverse chairs. We retrain related methods on our dataset and show a qualitative comparison using the same unseen chair and character starting position. ROM does not require contact labels as required by neural state machine. We generate more natural motion compared with SAMP. Roam outperforms couch in terms of generalization. Thanks for watching.